It's my pleasure to introduce our speaker, Pankaj Mehra. So Pankaj Mehra is the president and the CEO of the Elephance Memory, and he's also the part-time associate professor at the UC Santa Cruz. So Pankaj is the world-class expert in the storage system. He was the VP of the Samsung working on the memory, and also he was like the senior VP of many famous world-leading companies in the field. So today we are very excited to have him to talk about memory-centric system architecture. Okay, thank you.
And thank you for that introduction. We have some really interesting things to talk about. I tell people that it's a really great time to be working in memory. And, it's because for 40 years we have had basically the same architecture, one transistor, one capacitor, DRAM device attached to parallel buses. I'm reminded of talks that as Professor Michael J. Flynn became emeritus at Stanford, he gave an emeritus talk in the early 90s. And he was talking about, how everything about memory can get better except latency. And he showed latency was only improving at about 7% a year and not even. The problems in memory and the ideas even like pointers chasing are very old, and we have wanted some innovation in the memory side, but memory innovation was tied to processor innovation. And even today, when people are innovating like on things like disaggregated memory and CXL, Intel is in charge of the CXL standard, and they impose their view very strongly. So they're trying to keep processors smart and devices dumb, except academia is smarter, and we all know that function wants to gravitate to data, and it's important to think about device-side architecture, as many people in the room have been saying for years. So today's talk, there's a little byline there which says device side. I actually have only worked on devices since 2002 when I first met memory. And I always start my talk with a little jungle tale because, over the years I learned that logic and software are like dogs. And, you folks in the UK will understand that, if you have an orderly process and you do all the Pavlovian training, then your dog will follow one step behind you when you walk. But a cat goes everywhere. And so memory is very much the wild cat in data center. I learned the hard way that when you have to introduce new memory device technology, um, you build it, then your health team tells you how well you did, and then you build another one. And sometimes, you have memory, sometimes you have sensor. And Subhashish Mitra at Stanford was telling me that, when all fails, then we have battery. So, memory is all about how deeply circuit is penetrating charges. And we have had memory since we had batteries in Mesopotamia in a pot full of electrolyte. Okay. But there was no circuit penetrating the microcharges. So memory is about, trapping 7 electrons in a floating gate, and memory is about, holding fewer and fewer charges and trickling them under very fine control and sensing without disturbing and all this. Okay. So memory is really nasty, and we are going to begin today's talk by talking about how much of memory's problem really is memory device technology versus everything else. Okay, it's really important to understand that. We'll talk about a possible solution. I incorporated the company I'm leading right now in July, together with some students and faculty at UC Santa Cruz. We've been working on this. Our first papers are from 2017. So we've been working in the open. Even when I was at Samsung, I was publishing as an IEEE member. This is my own work in my own time. And I'll end the talk today with a little bit of trends and projections, sort of a view of the future. Okay. So let's get going. Okay. The slide on the left is actually, the part of the slide on the left is not my work. I've been involved in looking at workloads and what they are telling us about what we need from memory for a few years. I used to lead SanDisk's and then Western Digital's 5-year technology outlook process. So one of our favorite charts was from the IBM Power Systems team. They had done analysis of various workloads to see if you do these spider charts, then where would our needs be on memory capacity and memory bandwidth. But notice not the spider charts, but the categories the workloads are drawn from. Today, we would call these workloads HPC 5 years later, and all these other areas now have memory intensive workloads. So the data below is from a survey that Open Compute Project, which is a consortium of all the hyperscale companies. They formed a memory working group, a software-defined memory working group during the course of last year. And at last OCP conference worldwide, they announced that this has now become a full-blown initiative in hyperscale data centers. As part of this, Manoj Padekar from Facebook and other people shared some numbers about what is the new uh, way that we want to look at this picture. It's similar idea that you have memory, so you have cost and power, and you have capacity and latency. The same old issues that Professor Flynn taught us to talk about are still with us. But notice how more and more workloads like AI ML, where models are hitting, trillion parameters and not stopping, and database and general purpose dense virtualization with thousands of VMs launching every second in these large scale data centers. These workloads are very capacity driven, and they don't stress bandwidth or latency as much. In fact, the newest data, which I'm not at liberty to share with you from Google, but I encourage you to look for, a very large database conference paper where they will be sharing the latest numbers on how latency independent they can get their bandwidth utilization. So things are actually improving. Google wrote a paper in 2016, right about the time this study was published on the left, in which they harped on the attack of the killer microsecond. How many people in the room have read Luis Barroso's paper on killer microsecond? Okay. Yeah, if the rest of you need to read it, it's one of the most influential papers personally for me. And it does not mention memory. Okay. But if you talk to anybody in the industry today, the two things that are mentioned in the same breath are that killer microsecond paper and memory. Because what's about to happen to memory because of what we see at the bottom right of this chart is that finally we are trying to have bandwidth independent of latency because Intel is telling us that Moore's law is still alive. We can continue to have more and more cores per die. And Professor Kozirakis at Stanford, he wrote a very nice paper at HotOS 21 about freedom from context switches, which paper actually is neither about operating systems nor context switches. It's about what microarchitecture needs to do, so we will not have context switches. One of the projections is that we will have very high core count processors. We will come back to this topic at the end of the talk. But right now, I want to deep dive a little bit into the world of memory. So there are two things about memory, and we are going to take an excursion in the middle of the slide to kind of really understand what's the difference between the top row of this table-like uh, presentation that you see on this slide, and what's the difference versus the bottom row. Um, so the first thing about memory is how much it costs. Its cost used to go down with roughly the scaling of transistors. So, about every 1.5 years, we would have halving of cost. It completely stopped in 2015. We have basically had no decline in memory price. We have been at about $4 a gig for about 7 years now. Okay, so crisis, right? But we need to ask ourselves, this was one of the most optimistic periods for reducing the cost of memory because Optane was coming. Jim Handy, a memory industry analyst, had predicted that memory in 2020 will be 15 cents a gig. What happened? Optane was actually introduced with much fanfare by Intel. Actually, we in our 2020 Outlook at SanDisk, people who were from Matrix Semiconductor who had built 3D cross-point memory before for Nintendo cartridges. Strangely enough, it was OTP memory, one-time programmable memory. We knew that there will be no third generation Optane. In 2015, we knew this because we had built cross-point memories and we knew that 2 layers and 4 layers was practical. There was not going to be an 8 layer. And because they had to introduce it at 20 nanometer, at the time of introduction, which was aggressive, we knew there was not an aggressive roadmap of XY scaling for something that was a thermal element at the center of the device, which is a phase change, heating element that exists that goes between amorphous and crystalline phase. Okay. So in 2015, we predicted that Optane will die when it hits third generation, long before it actually happened. It did happen. Intel learned the hard way that new memory is very hard to introduce. That these people, hats off to them. They worked on it since the days of mnemonics when I first started to get interested in memory at Tandem, where I was looking for persistent memory to address low latency transactions. And I started becoming interested in these OUM, Ovonix Unified Memory, and all these things that later became Optane. But it took decades of really diligent work to get it out, and then it didn't work. The other thing about memory is that demand for memory has been exceeding supply for a long, long time. And so in the last few years of the pandemic, the demand was so far ahead of supply that companies started doing what airline companies do with petroleum. They started signing long-term agreements, meaning not only did we not have improvements in price, in some cases, as we are about to get the improvement in price because of supply-demand situation, there are LTAs in place that will prevent those improvements from being picked up by those who need to consume. Okay, that is the situation we are in. But this is half the problem. And interestingly, this is not uh, the worst part of the problem. Okay, so to understand the worst part of the problem, we need to look at what happens to memory as we buy it, software people. Okay, so I did some comparisons together with a product manager from Amazon's AWS business, where we looked side by side at Amazon instances and the underlying physical infrastructure. So the same EC2 instances, they differ only in the amount of memory. They have identical vCore counts, vCPU counts, and they're hosted on identical physical infrastructure. When you compare that side by side, you get the marginal cost of memory, which lies somewhere between 30 and $22.50 per gig per year to rent something that costs outright $4 a gig to buy. Okay, I'll let that settle in. $4 going in and $22.50 per year on the way out. Okay, so you might look at these numbers, right? And you might say, hey, it's just because these hyperscale companies are greedy. Okay, and I will argue that that's not the case. Okay, so two things about this slide. One is that the red herring on the slide is the top row, that the actual numbers in the data center say that the real problem is not the cost of memory. If it went to zero, we would still be stuck by the rest of what is in the table and which is the bulk of the cost. That bulk of the cost has its roots in how memory is deployed. Okay, so we got rid of sheet metal bundling of resources for storage, networking, and even accelerated compute. We have software-defined networking, we have software-defined storage, and as of Project Monterey at VMware and other similar things, we actually have virtualized and disaggregated GPU in chassis such as A100 and so on. In fact, in highly bespoke systems, like we have from Cerebrus, we even have things like Memory X. We have disaggregated memory because they have wafer scale compute engine. There is no DRAM on the Cerebrus WSE, for example. Okay, the Memory X node is separate. Memory X fabrics and their memory node is separate from the machine learning system. But for the most part, in the data center, we don't have disaggregation. So memory is deployed like servers used to be deployed in 2000, which is we have to deploy memory capacity where we need it, exactly where we need it. In fact, if it's anywhere else, we cannot use it, we cannot consume it or sell it. As a result, and these are, I've been told by my hyperscale colleagues that these numbers are very kind to the reality. Okay. So the real situation is only worse than what I'm saying here. I've been told by Microsoft architects, for example. And they've published that data. So if you look at Phil Bernstein's latest paper on CompuCache, you can actually find the numbers from them. Okay. 20 to 30% of the memory that they buy is in the wrong sheet metal box. And because of the way memory is sold and consumed, they cannot even sell it. Okay. Then what happens after they sell it? So if you are a buyer, you're building a software service. Okay. You go and you try to rent EC2 instances. What happens to you? You have to pick, am I buying a large, small, or extra large instance? So up front, you're making a choice of am I paying, for 32 gigs of memory or am I paying for 256? You're going to rent that memory up front. Then 75% of the apps that rent that memory will use less than 25% of it at any given point in time. Okay? Horrible, horrible economics of memory in the data center. So now that's good setup for what we are going to talk about. Because, when you first look at CXL, which is the technology that's going to supposedly help us out, it will make no sense to you if you don't have this context. Okay? So very important to take the lesson of the previous slide as we move forward. But first we look at what we do have right now. So memory, if these cartoon pictures, the blue boxes over here are sockets, the brown boxes are servers, these yellow boxes are DRAM DIMMs, and you have a memory controller on the CPU socket. You have cores, you have SRAM, which is in this bright orange, and as you attach memory to these parallel buses, which you have had for years now, the DDR buses, that's what we call memory today. If you want to reach out and touch another processor's memory, InfiniBand, which I worked on the first specification in 2000, is still about the only reasonable technology for remote memory access. And whether it's RDMA or Google RMA, uh, the way we touch the DRAM of another CPU is by doing RDMA read or RDMA write operations, if at all. Okay. So that's the world of memory today, and that's where all these problems are. Okay, so here comes this idea, brilliant idea in the industry, that we have been attaching memory to the PCI bus in the form of GPU, HBM, or just memory on the PCI bus. I built my first persistent memory prototypes in 2002 with PCI cards having a bunch of DRAM and battery. Okay, so we have had bad memory on the PCI bus. We even had the ability to address it byte by byte since 2002. Okay. And so people said, well, what's wrong with PCI bus? What's wrong with PCI bus is first byte latency. First byte latency was very high because you didn't know when a train of IO packets was going to cross in front of you because an SSD or a hard disk drive decided to do DMA, and you arbitrated behind that. So in CXL, they fixed that. They went to a flat architecture, which is pipeline networking, brought those principles back in from InfiniBand fabrics and into the PCI bus, and made it more suitable for memory attach. So now, CXL One of the killer applications of this CXL is these expansion memory buffers that attach to the new PCI Generation 5 with flit level architecture. And PCI 5 and beyond will now be more suitable for memory and accelerator attachment with coherence. So first generation CXL is these memory expanders that attach within the system. Okay, you still have the old RDMA networking if you want to go touch other memory. But at least now you start to solve the problem that memory capacity does not have to go up in powers of 2 like it had to with old DDR bus. The other thing is we don't need to keep scaling number of parallel wide channels to have more memory because we are pin limited to have more than 6 channels on most sockets or more than 8. But PCI buses, because they are wide serial links as opposed to parallel synchronous electrical links, you can have more of them on the same socket than you can have of DDR channels. So it's possible to have more capacity in the same square millimeter profile of the package. So, people are thinking that we will have midlife kickers in servers by attaching memory to the PCI bus when we run out of memory to attach on the DDR channels. Okay, that's where it starts. It's not very interesting from the point of view of solving those problems. So, whether it is CXL1, which is device-like deployment of memory, or DDR, a quick summary of what is going on is that we are here, we have all these bad deployment scenarios which give us all kinds of cost when we go to rent memory. In addition, we have very poor mechanisms because we have uniform scale out. Most applications, data intensive applications like Spark and so on, are scaling out because of memory capacity, not because of compute capacity. And when we do that, we end up moving data through these RPCs that goes between things like distributed machine learning frameworks. And as you have read in the Stanford papers that Pratiksha and other people have published there, the culprit in distributed machine learning frameworks is RPC. So RPC, serialization bound RPC, works at about a tenth of a gigabyte per second on modern Intel processors. It does not matter how fast a fabric you have. The cost of moving data in these systems is really, really high. And it's what plagues scale out infrastructure today. In addition to, the cost and deployment of memory, which is, very CPU affinity, high affinities to the CPU socket physically, and therefore all the evils that come with that. In addition, it's really hard to point to data that is far away from you. It's very hard to make calls with that data. We do parameter passing by value rather than parameter passing by reference when we do RPCs. In those 16, 17 deep call graphs, we are copying data around. Even if you go to any scale ray or any of the stuff that Stoica is talking about, the last copy is still actually a copy. Okay? So memory is really evil. Memory as a device, many people have talked about it. It's the root cause of our problems. And by the end of this talk, I'm hoping that I'll convince you that we have ingredients in place and we are only missing software to go to memory as a service as an architecture. So the first ingredient on that journey is CXL generation 3. Okay. Why did I miss CXL generation 2? Initially, the thought process in CXL was that CXL1 is PCI 5, CXL2 is PCI 6, which will be 64 gigatransfers per second, and then CXL3 will be PCI 7. They forgot how long it took to roll out PCI 3 because of all the standing waves and PHY level issues. Suddenly, industry was very optimistic that we were going to roll out a new PCI generation every 3 years. They forgot that PCI on copper has issues with retimers. A retimer introduces about 10 nanoseconds of latency in each direction and is required about every 15 centimeters or so, costs $100. They forgot all this. Okay, and suddenly we were going to have PCI 5, PCI 6, PCI 7, right, one after the other. So then, reality caught up. PCI 4 when it rolled out with very advanced Spectrum PHYs, controllers had to be re-engineered because the first controller, SSD controller we designed at Samsung for PCI 4 enterprise drives, which we tested with AMD, did not work with Intel's PCI 4 when it rolled out. Okay, why? PHY level issues. Do you think PCI 5, which doubles the data rate, is going to be any easier to roll out, or PCI 6, which doubles that again, is going to get any easier on copper? Silicon photonics was not within the horizon of this roadmap. So reality came home, and in August at Flash Memory Summit, the CXL consortium showed their face again and said, we are going to decouple CXL roadmap from PCI roadmap, thankfully. So CXL3, which is what industry really needs, which brings about disaggregation through multi-layers of switching, came ahead of PCI 7. CXL3 is compatible with PCI 5, PCI 6, and PCI 7 now, okay? And CXL3, so industry is kind of doing CXL1 plus right now, which is they absorbed CXL2 features in first generation parts that they're rolling out now. So it's CXL1 plus that is rolling out now. And then we'll go straight to CXL3, which will be these switched fabrics. You will not see very much CXL2 in the industry rollouts. Okay, so I'm not talking about it for that reason. CXL3 introduces these new kinds of switches. And the important thing, we don't have too much time to go into this, but the important things to understand is that the target latency of CXL3 switches, which carry memory traffic and coherence traffic as opposed to just IO traffic like PCI used to do in PCI 4 and before, is that 50 nanoseconds per switch per direction. Okay, so when you introduce one switch on an operation like load operation that will be happening through that fabric, you're going to have 100 nanoseconds of added access latency per switch that's in your route. The other thing to understand is these are very, very wide data paths to keep latencies this low. This is better latencies than Mellanox has, for example. Okay. So because of these wide data paths, there is going to be a trade-off between throughput and radix. So the radixes in the initial switches are not going to be very high, meaning the port counts of how many servers you can hook up through one switch. So either you are going to have to pay the penalty in depth, meaning you will incur these switch latencies again and again, or you are going to have to pay the penalty in bit, which is not a whole lot of servers will be able to connect with these high radix switches at low latency. Okay, so over time, photonics is supposed to be the white knight that saves this maiden in distress. We will see. Okay, CXL is kind of, I told you upfront that CXL is going to be ugly. Okay, so if I hadn't told you that uglier story about memory in the data center, you would be asking me, have you been bitten by a mad dog that you are talking to us about putting this kind of thing in the memory path where latency was only improving at negative 77% a year? And you come in and you start to introduce, 10 nanosecond per direction for retimer and 50 nanosecond per direction for switches. And I don't even know how many I will need to build anything at scale where I can start to see the benefits of disaggregation. Okay. So all this, caution aside, we are going to have disaggregated memory nodes for economic reasons because we want to pool memory and we want to start to get away from memory that is trapped in sheet metal so we can use it from anywhere. We want to have 100,000 server data centers with 512 gig or terabytes of memory. It's not possible to do terabytes of memory per server in old style deployments. The economics don't work. So we are going to get this and it's not going to be pretty. You are all with me? Okay. So here we are. Memory deployment will stretch across server boundaries and avoid stranded resources with CXL. We are going to have finally cost-efficient, cost-effective expansion to petabyte scale memory pools, which we all want for our in-memory workloads. We will have independent scaling of memory and compute. Very useful for scale-out applications where sometimes you have a big table that you have loaded and just a lightweight compute against it, like a filtering or aggregation operation. At other time, you're doing, deep iterative calculations on a little bit of data that you have just densified from wide sparse data sets. In that case, you need scaling of compute and not scaling of memory. Sometimes you need scaling of both compute and memory. We were stuck in an age where we had to scale both compute and memory. We are going to finally have independent scaling if we architect it right. And in addition, CXL is not just for memory. CXL also brings in the goodness of CAPI, OpenCAPI, and C6 and Gen Z. So it is going to enable coherent accelerators in addition to fabric memory, all good things. The hope is that for the first time in the technology industry, we will have coherence protocols that will be multi-vendor. We will have caching strategies, some LRU, some LFU, in the same system being kept coherent across a multi-vendor fabric. Okay, maybe. I think, Antonio, you have published on this topic, right? Multi-kernel, and you highlighted some of these issues. We
Yeah,
will see. We will see if this actually works out. So I'm very hopeful that they will talk to you and they will listen to you and learn ideas and cautions from your work. What I
And
see here, right? Let me pause for a second and give you a chance to comment on that. Sorry.
no, I was just saying, yeah, that I really hope so, because especially when you connect on shared memory different processing units that can be anything from CPU to specialized. At that point, you need to coordinate between each other, and I think that anything multiple kernel makes sense.
That's
But
right.
I had to continue. Yeah.
Yeah. So CPUs, GPUs, and other different things, one from NVIDIA, one from AMD, one from Xilinx, talking to, CPUs from Intel, AMD, and Ampere and Gravitons over a coherent standard, and somehow magically everything will work. I am very curious to know how many decades this will take.
That's fine. That's fine.
So this is the con, there is like 4 positive things and 1 negative things, and I don't know, how big this negative is, to tell you the truth. We are trying to figure out. Okay, so new devices, new APIs, and protocols are needed to make this all work, and it's because the latency, as I told you, will be higher. Okay, we are going to now stop being hardware people for a moment and think like software people. So if this is what the folks who live below us are going to serve up to us, what do we need to think about? Okay. So we are going to have data at a distance. It's going to be accessed from more than one server. Okay. And it's not going to be single system image. It is not, memory is not going to have mother may I relationship with the operating system anymore. If you, even from a failure point of view, security point of view, if you think about it, the operating system, its page table entries, its access control structures, which are all at process level, protect that memory. All of a sudden, if your thread, process, guest OS, hypervisor, or server crashes, that memory is still going to be around. Context switches might expose it in a multi-tenant setting to somebody else. What does that memory now need to do in order to be safe and secure in that multi-tenant fabric attached set? So there are performance things to do, which we want to see these optimizations, because when data is at a distance, we naturally want to see some data gravity and function shipping to that data. I hope we will not be zeroing out that memory between context switches by doing load store operations from a CPU to memory that is 400 nanoseconds. I think you all will agree with me. We want to take this, CPU-based serialization I don't think we will be putting buffers in that memory, converting them to network format, and then converting them back into uh, memory format just to restore pointers across different virtual to physical translation contexts. We want that to, when that memory is brought in near the CPU, we want caches to work. We want cache DRAM on the CPU to act as caches for DRAM on the CXL side. Okay, natural thing to expect. In fact, Intel and AMD at a panel we organized said pretty much that. They said this will not work unless DRAM caching in front of CXL caching works. Okay, so we want it to come back and without serialization, deserialization, come back with objects and data that are in CXL shared memory. When they come to the CPU, we don't want to be doing that at a tenth of a gigabyte per second. Okay. And as software people, we want to stay out of the load store data path as much as possible. Okay. The other thing is this stuff, Hynix predicted at Flash Memory Summit that the rollout will be spotty and unaligned was the word they used. The VP from Hynix who was talking at Flash Memory Summit that said that different people will be rolling out CXL 1, 2, 3. Some will have switches, only one layer permitted. Some will only have multi-port memory. Some will have full-blown fabrics. Some CPUs will have CXL 1. Some CPUs will have CXL 3. If you are a software developer, you don't want to be optimizing for every configuration. You want uniform APIs that work for distributed memory, which is what we have right now, and disaggregated memory, which we'll have, and every flavor of it. We are going to be spoiled for choice in the type of memory attaches we have after having only one for 40 years. So very, very important that we think about abstractions that work across a wide variety of scenarios. We want the kind of reference efficiency that we get with DSM and passing by reference other than passing by value, which we need for efficient calling. With the mobility of RPC, we want to be able to execute function at a distance for data gravity and function shipping. But we want that to work on virtual addresses and pointers that are meaningful everywhere. How do we make all this work? So this is where we started our work, and we are going to have a short introduction to this today. So I'm not giving a talk about MemOS. MemOS is actually a fork of some work we did at UC Santa Cruz, where Daniel Bittman is the PhD student that graduated. He's a co-founder with me at Elephance. And we can invite him back and he'll be glad to do his talk. But I'm going to summarize for you what this is. Okay. So it's an operating system that we started building a few years ago when we realized that memory is separating in space and time from the place where we compute on it. Okay. So if we have non-volatile memory at a fixed point in space, we can have the same data back when we won't have all the context in which that data was meaningful. So we wanted to rescue the context of pointer-rich data structures and save it in that non-volatile media so that when it comes back later in time, this was the original motivation for the Twizzler operating system when Daniel started working on it, and even before actually when Ethan and I were talking about it at OSGI 15. Okay. Later, as we started realizing that memory in space is as meaningful as in time, meaning sometimes we want to work with memory of a different node, and we started noticing all these inefficiencies. That's when we did our RPC paper in 2021 for hotnets, where we talked about how having global pointers from Twizzler will actually allow us to do pointer passing by reference rather than pointer passing by value. And now we are realizing that some of the choices we made, like having hardware support for capabilities for securing memory at a distance when we might not be around, but the data might still be around in non-volatile memory, is also a good idea for memory at a distance because of disaggregation. So if it's separated in space, the same idea is still meaningful. And then, we knew that we needed to take the abstractions that we are working on, and we needed to make them friendly to data center deployment. What does it mean to be friendly to data center deployment? So data centers have 100,000 servers and 5 people per administrative shift. If there is a problem due to memory leaks or safety issues due to not proper zeroing and data leaking out, there is nobody to attend to it. If disaggregated memory nodes do not take care of themselves, there will be nobody else to take care of them in the data center. So the security and safety principles that we had come up in storage mindset for Twizzler actually started to make sense to us when we started looking at CXL in 2019. So MemOS was the idea that the same things that Daniel did in Twizzler for storage, can we bring them into the CXL side? Okay. And so we had made choices like, started rewriting Twizzler and Rust because we wanted memory safety for pointer-rich data structures. And now those choices suddenly look very good, even for building an OS for disaggregated memory. Okay. So a quick summary of the data-centric programming principles in Twizzler. Okay. So, today data in processes is trapped in different translation contexts. And if you have to point to data from one process to another, we cannot really operate on it like memory. To do that, we will need pointers that are valid at every point in space and time in different translation contexts. So the basic idea of Twizzler was that, pointers that even need to work cross-device, not just cross-object and across process translation context. The translation context should be rescued from the process, and we should create for memory what S3 did for storage, which is we should make objects that, in addition to carrying the data of the objects, also carries the translation context with it. Okay, so we wanted object ID and offsets that actually work without being, untenable as pointers. So if we had a flat architecture like we do in everything from AS400 to other 96-bit pointer ideas that have been circulating in the industry for decades, we would basically flow the pipelines inside microarchitecture to untenable widths. So how do you solve the problem of keeping pointers significantly below 64 bits, like practical pointers are only 44 or 48 bits, not even 64, and still get object ID and offset like scheme that really gives you global identifiers? Okay, we could not afford both 128-bit object IDs and have pointers that were practical. Okay? So the idea in Twizzler is to embed something called a foreign object table inside every memory object. A foreign object table is only coming into play when a pointer points outside the object. Pointers inside the object have a special identifier that says they are offset only entities, and they work. And then there are special indications in the beginning of a pointer that say you should resolve it through foreign object table, which is captured with the object. Okay, so I'm rushing through this, but basically the object layout becomes like in a known place in an object there is foreign object table, there is other metadata fields in real Twizzler objects, and then there is data. Okay. So when you look at it, when self pointers within an object have a 0 at the beginning, like I was saying, and you just resolve and treat them, software can do this in a single-digit nanosecond. We built Twizzler and measured this. And so these pointers are extremely efficient on Intel CPUs. The other thing is that pointers that go across objects have some identifier in the beginning that designates them as pointers that are going cross objects. They resolve through the foreign object table entries that look like this. And when you go through that, that tells you that this is in a different object and provides the offset and permissions from accessing that within object. So it becomes the basis for doing both efficient page table entry management and becomes very device friendly in the sense that the number of page table entries you have are not proportional to the combined page tables of all the accessing CPUs. but rather proportional to the small word effects in the graph of objects that you are trying to capture in the device. Okay, so it's again, sorry for rushing through a little bit, but what Twizzler, which was originally created to run on CPUs in a distributed setting for managing memory that was separated in time, actually starts to make sense when you run it as an operating system on these disaggregated memory nodes to manage this memory. Okay. So that's what MemOS is. MemOS is this operating system that runs here on disaggregated memory nodes. And because of its global pointers, it delivers several benefits. So as I was saying, these pointers resolve with low software overheads. They can point within objects, or they can point cross objects or cross device. And now it becomes possible for a CPU over here that is talking to a MemOS managed device to say, hey, go chase down pointers or do a convolution or do depth first search on a graph and accumulate a metric on every node you encounter, for example, to calculate visiting probabilities for page rank and so on. Okay. So, we are going to rush through this a little bit, but the applications that are demanding this are kind of amazing. I've been going to some meetings with people like Tiger Graph and also going to the council meetings of this EKG council. People are building, like people in healthcare industry for real-time healthcare, people doing work on industry scale supply chains, people working on anti-fraud applications in financial and security industries. They have said no to joining tables because that doesn't happen in real time. They're moving to a new architecture where they build context that is alive. People who are building recommender systems for retail at Alibaba are doing this. People who are building real-time patient care systems at United Health Optum are doing this. And people in high-performance computing industry are doing this. Okay? So what are they doing? They're building these very, very large scale, petabyte scale graphs. In fact, their little benchmarks are like 36 and 38 terabytes of in-memory graph data. Previously, when we crawled data from a couple of hundred sources, we used to bring it into tables and then do joins on those tables. That is what gave us TPCH and data warehouse. And some people are still optimizing for that. That's not where the world is headed. The world is headed where when data comes in, you digest it immediately. You connect it with all the data you have seen before. And you're going to do connecting the dots not by doing table joins, but by doing link navigation, okay, in real time. Okay. So in that world, this new stuff that's coming in could work like this. So data like partitioned subgraphs will be living in these disaggregated memory nodes. Portions of the graph storage and processing engine will have been offloaded to the device itself. For example, depth first search and accumulate, a tiny inference operator, calculation of embeddings will be done in the disaggregated memory nodes rather than the compute nodes, which want to scale in proportion to the query. These memory nodes want to scale in proportion to the amount of data. And the illustrative interfaces of the kind, whether it is CRUD of memory objects or function offload, will be at this level of the abstraction. Okay. So in this situation, the work we are talking about will go and, for databases, it will allow you to do things like statistics offload, which is really important for online optimization of queries. Or for distributed recommender systems, it will let you calculate users like this and things like that by doing random walks on graphs, which is the basic mechanism for page rank and any other ranked recommendation. So do the necessary pointer chasing and graph convolutions in graph neural networks. And in other use cases like shared data clustering, handle things like low overhead transactions. And in microservice and RPC, which is 99% of the software world today, do the serialization avoidance that we were talking about. So customers in high performance computing industry who are building climate models and nuclear stockpile simulations. They have caricatured their applications into mini apps and then into benchmarks like Spatter, whose basic pattern is to do either strided access through sparse data or Laplacian calculated strides, which, if the data is sparse and graph oriented. So you end up with these index structures, and then you create densified data that will be operated on things like GPU at 100 times greater efficiency than you would if you were going to go work on that sparse data without some optimization. So those customers are now working with us, and they have made MemOS the software of choice to run on these memory nodes, so their CPUs and GPUs can run more efficiently. People like NVIDIA, CUDA team have looked at us and said the same thing. And then what will happen is that as you take graph neural networks and you offload convolutions, like graph convolutions, to these kind of devices, instead of the old way where you would have been sitting and manipulating that park memory from a distance with many round trips, moving data that you would only pick up pointers out of cache lines. So use maybe 4 bytes out of 64 that you have just put in at very low good part. You would, pollute your caches, you'd flood the network with useless data transfer. And because of the latency, starve your pipeline at front end and back end. As Khanif paper from Google explained in 2015, you will incur a lot of rule of three penalty, which would be really terrible. You have the goodness potentially of doing this at low latency near memory with high good put and independent scaling, like I was showing. Okay? So we are not stopping here. We want applications to be able to offload virtually addressed data and operations on that to this memory. And we are working with, some people like diffbot have actually written in memory databases in Rust. So we are exposing our Rust APIs to them. And for other people, we plan to develop Python and other bindings. There's a lot of work in front of us. But the idea is that at application level, you should be able to say convolve at a particular node in memory graph and have that be defined and shipped to devices where it can be operated on locally. The other thing is that because these pointers that we expose out of MemOS, they are global pointers. So instead of passing values like we do in RPC today, we can go inside frameworks like Rust, which are already trying to practice this idea and make them more efficient by just doing Twizzler pointer-based parameter passing by reference. And people like Microsoft are looking at the same idea. They've published this paper on CompuCache, where they have said that if you only had RDMA like IO interface and you were doing, this kind of stored procedure offload on pointer-rich data, you would have many, many round trips across the memory in a traditional RDMA setting. If you could ship function, but without cross-device pointer chasing, you would have 2 round trips. But if you have pointers with cross-device pointer chasing, you would end up with less than, this sort of ideal interface. So we are working with people like Phil Bernstein at Microsoft to actually deliver on their vision. So I'm going to close out today's talk. Basically, we began this work in 2017 around the idea of persistent pointers. In 2020, we started working on efficient RPC. Today, we are working on extending this to CXL with the idea that we can rendezvous globally addressed compute and data to achieve flexible placement of data and compute, sometimes moving data to the compute, sometimes moving compute to the data. At other times, when we are doing cross-node operations like joins, whose order is really dynamically determined, have the ability to rendezvous compute and data anywhere in the network, even on switches. And we have proven that with P4 programming of switches. And let me not repeat that. Why don't you guys take a quick picture of this slide and you can read this in your own time. We have been putting all our latest research on taking CXL infrastructure and applying these ideas in a special interest group that I lead at UC Santa Cruz. We are very current with what we publish there on our Google site. And we have a weekly meeting that will resume in early January with a talk by Antonio, actually. So we invite you to go visit that site. We have also, one of the things we have done in that site is looked at how the OS is evolving, like around heterogeneous memory management through contributions from people like NVIDIA to respond to this new memory architecture, both in the data plane and in the control plane, by taking long-term things like instruction set architecture improvements and short-term things like, just setting up discovery and configuration of these memories as ranges on demand. So again, I'm not going to dwell on that too much. The basic thing we are looking at is looking at this new memory from both the CPU's point of view, where it adds capacity, but at the cost of latency, and from the device point of view, where it brings the possibility of near memory accelerator, provided you can take care of virtual address translation and you can develop the right kind of interfaces that applications will use. Our long-term projection is to look at the broader discipline of data center design and architecture as two planes, which is basically an infrastructure plane and the software defining plane. So we think that memory virtualization instead of hierarchies will move more towards tiering, just because I said we'll be spoiled for choice by the amount of memory latency options that we will have and attach options we will have. So that's evident in the work to us on HMM. So there will be new service orchestration and scaling disciplines also because of independent scaling of memory and compute. And we think that memoryness will be pervasive, that you will be able to address more and more of data center memory using memory semantic rather than IO semantic, which has some natural advantages in terms of optimizations and such. We really like the work that Kunle is doing at Samba Nova, for example, and hope to embrace some of those ideas and bring them into MemOS. And then, we hope finally that the beneficiary will be things like databases and other data infrastructures like Ray and Kafka and so on. Okay. So we are projecting that in 2025, couple of years from now, there will be still mainly DRAM, but the DRAM will start to attach through compressed or reused memory way to bring down the cost. So when memory is decommissioned from data center servers and new Intel CPUs are brought in, the old DDR4 memory will go into these disaggregated DRAM and basically at zero cost give you additional fabric attached memory. Because of the distance, it will be possible to go to 1.5 to 2 times capacity by adding compression within that latency path. It's possible. So we will get very cost efficient petabyte pools. We will start to move towards memory as a service if they actually listen to us and start to bring us into some of these memory nodes. And we think that, in a nutshell, memoryness will be available to us at 1 microsecond latency, like Luis Barroso predicted in his killer microsecond paper, at about 3 meters, which means through these expanders of CXL1, first generation multi-port devices, and even one layer of switches, such as CXL3 will have. We think there will be a pivot in 2025 as CXL ramps up. This pivot will create a fresh opportunity for storage class memories to come back. It was almost impossible to deploy a new memory on old DDR attach because it was so synchronous and caused microarchitecture pipelines to hold their breath, while slow, cheaper, and denser memory took its time serving up memory accesses, especially write accesses. Okay. Asymmetry of read and write was really difficult to accommodate in DDR, but its CXL is engineered for memory at a distance, for memory that is asymmetric. Compression, for example, is asymmetric access on read and write. And the braid model work that Yuvraj presented was really music to my ears, I should say. And I really commend you on the work you've been doing in ICSA. And I hope we'll have a chance to collaborate and work on, this vision of the future where I think accidentally we have found each other very aligned in what we want to do. Let me stop there. Thank you. Thank you.
Okay, do you have time for maybe 5 minutes for questions?
Yeah, I think so, yeah.
Okay, do you guys want to start or can I? Okay. So maybe I start with a question. So okay, very interesting talk. Thank you very much. I think, as you said, it's very aligned also to at least my vision. So I was very curious about the fact that you showed the MemOS is on the memory board in some sense. So do you already have hardware on this, or you are sort of simulating the hardware because it's not ready yet?
I work with memory interface chip companies, and commercially, we are working on SoCs that are being engineered for this with ARM and with memory interface chip companies, and would love to collaborate with you because we know that you have good relationship with ARM.
Yeah, yeah, same. Okay, so another question very quickly. So, okay, indeed, I read the paper from Twizzler, but one thing that is not very clear to me is like, so I understand the operating system, I understand the API, I understand the sort of virtual table, but do you have a special compiler? Or, okay, because Rust, so did you modify Rust in order to compile with those pointers? Okay.
Again, these questions, Twizzler specific questions, I suggest that the next time we meet, if the collaboration is actually taking off, then after you come back and talk, I'll make sure Daniel attends your talk. And then at a suitable time, we can invite Daniel back to do a follow-up talk. In fact, this is how we kicked off our VMware collaboration in 2021, which is I gave the talk in August, then Daniel followed up with a talk in September. And we had a good collaboration with VMware Research Group as a result of all that.
Well, fantastic. Yeah, thank you very much.
Sure.
I have a question.
Yeah, please tell me your name. I see you in a very small few pixels, so hard to realize who is this.
Kareem.
Kareem, yeah.
He's working with me.
Okay, great.
Is it a use case for software to partition a logical CXL memory device?
I think the devices don't want to impose policy. They want to expose mechanism. So generally speaking, in a software-defined data center, the control plane and the data plane want to collaborate on that partitioning. So largely things like fabric managers, which are owned by people who buy that memory capacity and deploy it, want to come in and expose hundreds of gigabyte wide address ranges as hot pluggable memory. That's memory that's available on demand to those people who want to buy it, not upfront in the old way, but as a on-demand fungible resource in the new way, memory as a service.
So basically, the operating system asks the fabric manager to allocate the memory for it.
Yeah, that's half the answer. The other part of the answer is now, somebody like a slab allocator in a data infrastructure picks that up, and it gets a portion of that address range that the hypervisor gives it. Okay, then it supports mallocs, whether they are from a JVM or a JavaScript VM or other heap allocator out of that. So that memory gets partitioned through multiple tiers of memory allocation. The vision that is communicated in both Hynix and Samsung SDKs, as they have put out first generation memory expanders together with software, is to replace JE-malloc and CE-malloc, use JE-malloc and CE-malloc to replace malloc itself, and to combine that with improvements in libnuma to select policy for when should we allocate data structures in this far memory, which has a different latency and bandwidth profile compared to everything else. Facebook, in their TPP paper, have published that they find it useful to put not anonymous allocations, but file-backed allocations into far memory because of their relatively cool access characteristics. So people are still working on these ideas. There are some ideas that are HMM centric. There are some ideas that completely bypass HMM. And we are watching all this and trying to see how the OS layer will settle in terms of discovering, allocating that memory to hypervisors. How will hypervisors settle and give those to guests? And then how will those guests give that to applications? This is still forming.
Yeah, this makes sense from a single single operating system instance, but what if multiple operating systems share access to the same CXL device? How would you manage that?
You would end up writing the next generation of Omega Kubernetes and Docker, and somebody from this PhD group will have a really, really interesting PhD thesis for heterogeneous infrastructure knapsack problem. Maybe it will be a thesis in combinatorics. Maybe it will be a thesis in the next generation cloud native compute foundation work. I don't know. There's a lot of opportunity there and very few answers.
Thank you.
Yeah.
So this talk actually is very interesting because my group actually has been also working a lot on the deep learning recommender system, graph learning, and also the sparse transformer, right, which can all potentially largely benefit from the SL because of the sparsity in the workload, right? So recently, actually, we are also looking for if somehow we can also try to demonstrate if this AI workload can benefit from the SL, but we have a little bit struggling to find out how I can demonstrate this, right? So do you have any suggestion, right? So given the current commercial market, right? So if that's like any way we can demonstrate the benefit of porting this AI workload onto this new hardware. Yeah, thank you.
I think that more memory, and especially memory in the middle and more efficient RPC, will have good benefit for AI. The early answers are in the papers that were published at Hot Chips by Cerebras, in the sense that when they thought about function near memory, because more and more if you do a highly integrated iterative infrastructure where you are processor centric and you have only SRAM which operates at the speed of the processors and no DRAM locally, then because you have memory at a distance, you don't have enough memory to even hold all the weights. The models are too big for even a wafer scale Cerebras engine. So they moved away from installing weights and flowing activations to accumulating activations and flowing weights and gradients. And in the course of flowing weights and gradients, they found it useful to push gradient combining in the back pass of backpropagation to the device. I think this is the beginning of ideas for AI and machine learning, which is how could they benefit from memory architecture that supports disaggregation and offload. I have published a couple of books on machine learning and built several systems. And I would like to take time to go through the ideas and use cases in some detail, whatever you're thinking, and maybe revisit that more one-on-one than in today's setting.
Sure. Thank you. So my last question is that you also mentioned that the metaverse and also the intelligent robot arms will be the killer application for the memory as a service, right? Could you actually elaborate this a bit more? Because
yeah, there are several reasons for this. Okay, I think because metaverse happens in the real world, it does not happen in data centers. And it's very latency sensitive application. And I doubt that photorealistic rendering and some of the things like augmented presentation of information within the context of, a machinist working on a car, etc., will happen from a distance like data center distance. So I think memory, because intelligence and simulation will be in the loop, so AI will be in the simulation loop and simulation will be in the AI loop. And all of this will be happening in the context of cyber physical, not just, sort of screen-based at a distance interfaces that we have today. So I think because of that, the compute core will be extending out and meeting applications closer to the edge. This is not my vision. This is the vision of automotive industry, and even Facebook, have said that if they could get a good price for memory, they would actually build a lot more edge data centers that they have been able to. So this idea of surround and experiential memory that follows you wherever you go and delivers functions is one consideration. The other consideration is COPA and other privacy acts around the world. The CEO of Apple, Tim Cook, and other people have said that they will be doing more processing on the phone device and do less data shipping. But we know from the projections from Google that the models that they will want to work with are growing faster than the amount of memory is growing in the world. People such as Ramesh Ruskar at MIT and his students who have been working closely with me, what they are working on is split ML and fed ML. And I think that some of this will be in the context of split ML and fed ML as well, that we will need memory as a service very close to the edge. So those are my quick comments on that.
I see. Okay.
Do we have time for one more question?
Yes.
Maximum.
Yeah, one. Yeah.
So I would like to know your opinion on one thing. What do you think is the role of one-sided RDMA in the context of CXL?
When we built MemOS, we knew that initially we will only have one-sided memory operations, which are all hardware on one side and just software, very user mode software because of IOU ring and other improvements in Linux on the access side. But this is not new. We engineered persistent memory when I first worked on it in 2002 and built persistent memory manager and the first persistent memory file systems that we published in 2004 in my IEEE work. We built it for this kind of one-sided RDMA. So CXL is different, right? CXL is all hardware data path. It's actually true load store for memory. So you don't issue by queuing read and write requests. You issue by actually executing load and store instructions. There's a little bit of debate about this in the industry right now, okay, especially for compressed memory. So if you look at HMM, which is sort of the core of where Linux work around memory management is happening for CXL, it is able to go to one hop for memory as memory. But if you have two hop for memory or you have compressed memory, the number of nanoseconds it takes to get there because of what I explained at the beginning of the talk. Linux and modern processors, current processors, are not able to deal with memory that is 350, 400 nanoseconds away and continues to be that way, not just for one or two accesses like would be in NUMA, but continues to be that far away at microsecond grain. We don't have that architecture today. So Linux cannot help it. So Linux stops and has to concede to other interfaces, for example, behind ZSwap or behind other ways of touching compressed cache lines. There is good work at CMU in that area in terms of anticipating what future projects will look like. You can, read some of the PDL papers that are coming out in this area on how, as events happen in the memory hierarchy, you can have callbacks to the application. So whether it will be RDMA-like interfaces where you have, submission queues and completion queues that take in read and write requests in the submission queue, and then notify you back in user mode very efficiently with one context switch through the completion queue, or whether we will have callback interfaces like some of the new work from CMU is anticipating. I think there will be one of every kind for the foreseeable future. So in MemOS, we have resolvers. Okay, I didn't go into that today. You can ask Daniel when he comes back to talk. Basically, when we resolve addresses, if they are simple Twizzler pointers, we address them like I was showing you in my quick slides today. Okay, but if you have, PGAS, like how HPC partition data in distributed systems and supercomputers, or you have RDMA, there is nothing that prevents software from telling Twizzler, here is a piece of code on how you should resolve a pointer. And we can allow applications to inject certain qualified code into our resolvers so that you can write your own pointer resolvers. The thing to understand about MemOS and your question is that MemOS injects itself in the memory access path on only three events. Okay, one is allocation, the other is deallocation, and number three is pointer dereferencing. These are exactly the same three that Google used in their far memory work. when they started using Z-swap as for memory, and they introduced RMA, remote memory access, as for memory. We think that this is actually a reasonable interface set to work on, and this is the direction of our future work also. There is other things to talk about, but there's no time today.
Thanks.
Thank you all.